Weak isolation levels. If two transactions don't touch the same data, they can safely be run in parallel, because neither depends on the other. Concurrency issues. Race conditions only come into play when one transaction reads data that is concurrently modified by another transaction, or when two transactions try to simultaneously modify the same data. Concurrency bugs are hard to find by testing, because such bugs are only triggered when you get unlucky with the timing. Such timing issues might occur very rarely, and are usually difficult to reproduce. Concurrency is also very difficult to reason about, especially in a large application, where you don't necessarily know which other pieces of code are accessing the database. Application development is difficult enough if you just have one user at a time. Having many concurrent users makes it much harder still, because any piece of data could unexpectedly change at any time. For that reason, databases have long tried to hide concurrency issues from application developers by providing transaction isolation. In theory, isolation should make your life easier by letting you pretend that no concurrency is happening. Serializable isolation means that the database guarantees that transactions have the same effect as if they ran serially, i.e. one at a time, without any concurrency. In practice, isolation is unfortunately not that simple. Serializable isolation has a performance cost, and many databases don't want to pay that price. It's therefore common for systems to use weaker levels of isolation, which protect against some concurrency issues, but not all. Those levels of isolation are much harder to understand, and they can lead to subtle bugs, but they are nevertheless used in practice. Concurrency bugs caused by weak transaction isolation are not just a theoretical problem. They have caused substantial loss of money, led to investigation by financial auditors, and caused customer data to be corrupted. A popular comment on revelations of such problems is use an ACID database if you're handling financial data. But that misses the point. Even many popular relational database systems, which are usually considered ACID, use weak isolation, so they wouldn't necessarily have prevented these bugs from occurring. Rather than blindly relying on tools, we need to develop a good understanding of the kinds of concurrency problems that exist and how to prevent them. Then we can build applications that are reliable and correct, using the tools at our disposal. In this section, we will look at several weak non-serializable isolation levels that are used in practice, and discuss in detail what kinds of race conditions can and cannot occur, so that you can decide what level is appropriate to your application. Once we've done that, we will discuss serializability in detail. See serializability on page V. Some databases support an even weaker isolation level called read uncommitted. It prevents dirty writes, but does not prevent dirty reads. 251. Our discussion of isolation levels will be informal, using examples. If you want rigorous definitions and analyses of their properties, you can find them in the academic literature. Read committed. The most basic level of transaction isolation is read committed.v. It makes two guarantees. When reading from the database, you will only see data that has been committed, no dirty reads. When writing to the database, you will only overwrite data that has been committed, no dirty writes. Let's discuss these two guarantees in more detail. Imagine a transaction has written some data to the database, but the transaction has not yet committed or aborted. Can another transaction see that uncommitted data? If yes, that is called a dirty read. Transactions running at the read committed isolation level must prevent dirty reads. This means that any writes by a transaction only become visible to others when that transaction commits, and then all of its writes become visible at once. This is illustrated in figure 7-4, where user 1 has set x equals 3, but user 2 get x still returns the old value, 2, while user 1 has not yet committed. Figure 7-4, no dirty reads. User 2 sees the new value for x only after user 1 transaction has committed. There are a few reasons why it's useful to prevent dirty reads. Figure 7-5. With dirty writes, conflicting writes from different transactions can be mixed up. If a transaction needs to update several objects, a dirty read means that another transaction may see some of the updates but not others. For example, in figure 7-2, the user sees the new unread email but not the updated counter. This is a dirty read of the email. Seeing the database in a partially updated state is confusing to users and may cause other transactions to take incorrect decisions. If a transaction aborts, any writes it has made need to be rolled back, like in figure 7-3. If the database allows dirty reads, that means a transaction may see data that is later rolled back, i.e. which is never actually committed to the database. Reasoning about the consequences quickly becomes mind-bending. No dirty writes. What happens if two transactions concurrently try to update the same object in a database? We don't know in which order the writes will happen, but we normally assume that the later write overwrites the earlier write. However, what happens if the earlier write is part of a transaction that has not yet committed, so the later write overwrites an uncommitted value? This is called a dirty write. Transactions running at the read committed isolation level must prevent dirty writes, usually by delaying the second write until the first write's transaction has committed or aborted. By preventing dirty writes, this isolation level avoids some kinds of concurrency problems. If transactions update multiple objects, dirty writes can lead to a bad outcome. For example, consider figure 7-5, which illustrates a used car sales website on which two people, Alice and Bob, are simultaneously trying to buy the same car. Buying a car requires two database writes. The listing on the website needs to be updated to reflect the buyer, and the sales invoice needs to be sent to the buyer. In the case of figure 7-5, the sale is awarded to Bob because he performs the winning update to the listings table, but the invoice is sent to Alice because she performs the winning update to the invoices table. Read committed prevents such mishaps. However, read committed does not prevent the race condition between two counter increments in figure 7-1. In this case, the second write happens after the first transaction has committed, so it's not a dirty write. It's still incorrect, but for a different reason. In preventing lost updates on page 242 we will discuss how to make such counter increments safe. Implementing read committed. Read committed is a very popular isolation level. It is the default setting in Oracle 11g, PostgreSQL, SQL Server 2012, MemSQL, and many other databases. Most commonly, databases prevent dirty writes by using row-level locks. When a transaction wants to modify a particular object, row, or document, it must first acquire a lock on that object. It must then hold that lock until the transaction is committed or aborted. Only one transaction can hold the lock for any given object. If another transaction wants to write to the same object, it must wait until the first transaction is committed or aborted before it can acquire the lock and continue. This locking is done automatically by databases in read committed mode or stronger isolation levels. How do we prevent dirty reads? One option would be to use the same lock, and to require any transaction that wants to read an object to briefly acquire the lock and then release it again immediately after reading. This would ensure that a read couldn't happen while an object has a dirty, uncommitted value, because during that time the lock would be held by the transaction that has made the write. However, the approach of requiring read locks does not work well in practice, because one long-running write transaction can force many read-only transactions to wait until the long-running transaction has completed. This harms the response time of read-only transactions and is bad for operability. A slowdown in one part of an application can have a knock-on effect in a completely different part of the application due to waiting for locks. Roman 6. At the time of writing, the only mainstream databases that use locks for read committed isolation are IBM DB2 and Microsoft SQL Server in the read committed snapshot equals off configuration. For that reason, most databases prevent dirty reads using the approach illustrated in figure 7-4. For every object that is written, the database remembers both the old committed value and the new value set by the transaction that currently holds the write lock. While the transaction is ongoing, any other transactions that read the object are simply given the old value. Only when the new value is committed do transactions switch over to reading the new value. Snapshot isolation and repeatable read. If you look superficially at read committed isolation, you could be forgiven for thinking that it does everything that a transaction needs to do. It allows aborts required for atomicity. It prevents reading the incomplete results of transactions, and it prevents concurrent writes from getting intermingled. Indeed, those are useful features and much stronger guarantees than you can get from a system that has no transactions. However, there are still plenty of ways in which you can have concurrency bugs when using this isolation level. For example, Figure 7-6 illustrates a problem that can occur with read committed. Figure 7-6, read skew. Alice observes the database in an inconsistent state. Figure 7-7. Implementing snapshot isolation using multi-version objects. Say Alice has $1,000 of savings at a bank, split across two accounts with $500 each. Now a transaction transfers $100 from one of her accounts to the other. If she is unlucky enough to look at her list of account balances in the same moment as that transaction is being processed, she may see one account balance at a time before the incoming payment has arrived with a balance of $500. And the other account after the outgoing transfer has been made, the new balance being $400. To Alice it now appears as though she only has a total of $900 in her accounts. It seems that $100 has vanished into thin air. This anomaly is called a non-repeatable read or read skew. If Alice were to read the balance of account 1 again at the end of the transaction, she would see a different value $600 than she saw in her previous query. Read skew is considered acceptable under read committed isolation. The account balances that Alice saw were indeed committed at the time when she read them. The term skew is unfortunately overloaded. We previously used it in the sense of an unbalanced workload with hotspots. See skewed workloads and relieving hotspots on page 205, whereas here it means timing anomaly. In Alice's case, this is not a lasting problem, because she will most likely see consistent account balances if she reloads the online banking website a few seconds later. However, some situations cannot tolerate such temporary inconsistency. Backups. Taking a backup requires making a copy of the entire database, which may take hours on a large database. During the time that the backup process is running, writes will continue to be made to the database. Thus, you could end up with some parts of the backup containing an older version of the data and other parts containing a newer version. If you need to restore from such a backup, the inconsistencies such as disappearing money become permanent. Analytic queries and integrity checks. Sometimes, you may want to run a query that scans over large parts of the database. Such queries are common in analytics. See transaction processing or analytics on page 90, or may be part of a periodic integrity check that everything is in order. Monitoring for data corruption. These queries are likely to return nonsensical results if they observe parts of the database at different points in time. Snapshot isolation is the most common solution to this problem. The idea is that each transaction reads from a consistent snapshot of the database. That is, the transaction sees all the data that was committed in the database at the start of the transaction. Even if the data is subsequently changed by another transaction, each transaction sees only the old data from that particular point in time. Snapshot isolation is a boon for long-running, read-only queries such as backups and analytics. It is very hard to reason about the meaning of a query if the data on which Roman 7, to be precise, transaction ID are 32-bit integers, so they overflow after approximately 4 billion transactions. PostgreSQL's vacuum process performs cleanup, which ensures that overflow does not affect the data it operates is changing at the same time as the query is executing. When a transaction can see a consistent snapshot of the database, frozen at a particular point in time, it is much easier to understand. Snapshot isolation is a popular feature. It is supported by PostgreSQL, MySQL with the InnoDB storage engine, Oracle, SQL Server, and others. Like read committed isolation, implementations of snapshot isolation typically use write locks to prevent dirty writes. See implementing read committed on page 236, which means that a transaction that makes a write can block the progress of another transaction that writes to the same object. However, reads do not require any locks. From a performance point of view, a key principle of snapshot isolation is readers never block writers and writers never block readers. This allows a database to handle long-running read queries on a consistent snapshot at the same time as processing writes normally, without any lock contention between the two. To implement snapshot isolation, databases use a generalization of the mechanism we saw for preventing dirty reads in Figure 7-4. The database must potentially keep several different committed versions of an object, because various in-progress transactions may need to see the state of the database at different points in time. Because it maintains several versions of an object side by side, this technique is known as multi-version concurrency control (MVCC). If a database only needed to provide read-committed isolation, but not snapshot isolation, it would be sufficient to keep two versions of an object, the committed version and the overwritten but not yet committed version. However, storage engines that support snapshot isolation typically use MVCC for their read-committed isolation level as well. A typical approach is that read-committed uses a separate snapshot for each query, while snapshot isolation uses the same snapshot for an entire transaction. Each row in a table has a created by field, containing the ID of the transaction that inserted this row into the table. Moreover, each row has a deleted by field, which is initially empty. If a transaction deletes a row, the row isn't actually deleted from the database, but it is marked for deletion by setting the deleted by field to the ID of the transaction that requested the deletion. At some later time, when it is certain that no transaction can any longer access the deleted data, a garbage collection process in the database removes any rows marked for deletion and frees their space. An update is internally translated into a delete and a create. For example, In Figure 7-7, Transaction 13 deducts $100 from Account 2, changing the balance from $500 to $400. The accounts table now actually contains two rows for Account 2, a row with a balance of $500 which was marked as deleted by Transaction 13, and a row with a balance of $400 which was created by Transaction 13. Visibility rules for observing a consistent snapshot. When a transaction reads from the database, transaction ID are used to decide which objects it can see and which are invisible. By carefully defining visibility rules, the database can present a consistent snapshot of the database to the application. This works as follows. At the start of each transaction, the database makes a list of all the other transactions that are in progress not yet committed or aborted at that time. Any writes that those transactions have made are ignored, even if the transactions subsequently commit. Any writes made by aborted transactions are ignored. Any writes made by transactions with a later transaction ID, i.e. which started after the current transaction started, are ignored, regardless of whether those transactions have committed. All other writes are visible to the application's queries. These rules apply to both creation and deletion of objects. In Figure 7-7, when Transaction 12 reads from Account 2, it sees a balance of $500 because the deletion of the $500 balance was made by Transaction 13 according to Rule 3. Transaction 12 cannot see a deletion made by Transaction 13, and the creation of the $400 balance is not yet visible by the same rule. Put another way, an object is visible if both of the following conditions are true. At the time when the reader's transaction started, the transaction that created the object had already committed. The object is not marked for deletion, or if it is, the transaction that requested deletion had not yet committed at the time when the reader's transaction started. A long-running transaction may continue using a snapshot for a long time, continuing to read values that from other transactions' point of view have long been overwritten or deleted. By never updating values in place, but instead creating a new version every time a value is changed, the database can provide a consistent snapshot while incurring only a small overhead. How do indexes work in a multi-version database? One option is to have the index simply point to all versions of an object and require an index query to filter out any object versions that are not visible to the current transaction. When garbage collection removes old object versions that are no longer visible to any transaction, the corresponding index entries can also be removed. In practice, many implementation details determine the performance of multi-version concurrency control. For example, PostgreSQL has optimizations for avoiding index updates if different versions of the same object can fit on the same page. Another approach is used in CouchDB, Datomic, and LMDB. Although they also use btrees, see btrees on page 79. They use an append-only /copy-on-write variant that does not overwrite pages of the tree when they are updated, but instead creates a new copy of each modified page. Parent pages, up to the root of the tree, are copied and updated to point to the new versions of their child pages. Any pages that are not affected by a write do not need to be copied and remain immutable. With append-only btrees, every write transaction or batch of transactions creates a new btree root, and a particular root is a consistent snapshot of the database at the point in time when it was created. There is no need to filter out objects based on transaction ID, because subsequent writes cannot modify an existing btree. They can only create new tree roots. However, this approach also requires a background process for compaction and garbage collection. Snapshot isolation is a useful isolation level, especially for read-only transactions. However, many databases that implement it call it by different names. In Oracle it is called serializable, and in PostgreSQL and MySQL it is called repeatable read. The reason for this naming confusion is that the SQL standard doesn't have the concept of snapshot isolation, because the standard is based on System R's 1975 definition of isolation levels, and snapshot isolation hadn't yet been invented then. Instead, it defines repeatable read, which looks superficially similar to snapshot isolation. PostgreSQL and MySQL call their snapshot isolation level repeatable read, because it meets the requirements of the standard, and so they can claim standards compliance. Unfortunately, the SQL standard's definition of isolation levels is flawed. It is ambiguous, imprecise, and not as implementation independent as a standard should be. Even though several databases implement repeatable read, there are big differences in the guarantees they actually provide, despite being ostensibly standardized. There has been a formal definition of repeatable read in the research literature, but most implementations don't satisfy that formal definition. And to top it off, IBM DB2 uses repeatable read to refer to serializability. As a result, nobody really knows what repeatable read means.